So what we will do in this Zoom session is we'll quickly go through the examples that we have discussed in the last Zoom session, as well as in the recorded video lecture, which were the exercises that were given, and then we will move on. Can anyone quickly tell me the definition for 1D Fourier transform? What was the variable we were using? So f of x is equal to integral over, what is the integrand here?
kx
Kx, varying from
minus infinity to infinity.
minus infinity to plus infinity. F of kx is the kx ky space we are writing. So we are writing it as f of kx into exponential of j times 2 pi kx into x and integrating with respect to dkx, right? That was the synthesis equation. And then this Fourier equation in the frequency spectrum, we are writing it as where now the variable we want it in terms of kx, so you would be varying x, and then you start with the original function in the spatial domain f of x, then complex exponential conjugate will be there, so minus 2 pi kx into x. You need to get it in terms of kx, so you integrate it with respect to x, right? These were the definitions. Then what we were doing, we were taking a look at some of the examples. What was the first one example that was given in the recorded video lecture?
Recto function.
Right, right, good. So it is referred to as box function or rect function. How does it look like? You have just 1D variable here. So its value is 1 from x equal to?
Minus half to plus half.
Right, from minus half to plus half. This is 1, outside it is 0. So what would be getting as a result of this in the Fourier domain now? So this is what you have as this rect function here. So for rect function, if you take the CTFT of it, what would we get here? Sinc function, right? How is sinc function? There are a couple of slight variations in the definitions of sinc function. What do we mean by sinc function here? Sine of
x by pi.
right, sine of pi x by pi x. So is this function symmetric? Yes. How can you say sine is an odd? Here you will get sine of minus pi x as minus sine pi x, and there is one more negative here, so that would make it even function, right? So this is what you get as sinc of x. What's the maximum value here?
1.
1, correct. So this is at 0. What would be the value here where it is getting 0? Sinc of, I should have written this, what instead of x, what should I write here? Sinc of
Kx.
Yeah, that's right. Sinc of kx. Because we are in the frequency domain. So let me do the same thing here. Sinc of pi times kx by pi times kx. Now I would call it as kx. So this value here is, at this point is
1.
Yeah, right. All integers, it would become 0. This would so on. Yeah, it should be symmetric, although it is not symmetric in the way I have drawn, but it should be ideally symmetric, right? Now, if I ask you, the second one would be sinc of x. What would be the CTFT now?
Rectangular. Box of kx.
Very good. Box of kx. See, all you need to do is whichever is there on the right side, if that function, you flip that function, and for that, whatever is there on the right hand side would be your CTFT. So once you compute one pair, other pair comes for you for free, that combination. In this function, sinc of x being even function, so even if you flip it, you get the same thing. So you are getting a box function now. Now the variable being in the frequency domain, you are changing the variable from x to kx, correct? So third one, delta of x. What was the CTFT of it?
1.
Right. Good. So I don't think I need to derive this because you know it from your earlier courses itself, right? Then for 1, what is the CTFT?
Delta of kx.
Very good. Delta of kx. So here the nice thing is that 2 pi also, that multiplication factor also goes off. This 1 anyway, if you are flipping it, that was still 1, right? So you have the delta of kx nicely. Then the other one we had a look at is e power minus pi x square. So what did we say about its CTFT? E power?
E power minus pi kx square.
Right, good. Does any of you want me to quickly go through it?
Yes, sir.
Okay. So what we need to do now, we need to find out the Fourier transform for this. This would be variable for us is x varying from minus infinity to plus infinity, e power minus pi x square multiplied with e power minus
Minus
j.
j
2 pi
2 pi x.
kx
Right. Integrated with respect to the variable dx, right?
dx.
So how could I write this out? E power minus, I can take pi also out. This would become x square,
Plus j 2k x
right, right, plus 2 times j k subscript x into x. That's what it is going to be. So can I now write this as x is varying from minus infinity to plus infinity, e power minus pi of, so this you want to write it as just a square term and another subtract it from the other term kx, because that is something I could take out because the integrand here is with respect to x. So what the way I would like to write here is x plus what would be the other term, so that I will get a square plus 2ab.
jkx jkx
J subscript kx, good,
whole square
whole square minus what?
pi kx square.
Pi anyway I kept common here.
Okay. Plus no
Minus na?
kx plus kx square. Kx square.
Minus kx square, right?
No sir, plus will come sir.
Yeah, you are right. Plus kx square. That's right. That's right. It's because j square is there, na? Very good. Yeah. Kx square integrand with dx. Now can I take this term out? Yes, I can take it out. So that would bring me e power minus pi kx square into, let me call this as something as y. Okay, I could do some other complex number y, e power minus pi y square into, even if I call it as y integrand, yeah, this would be still dy. This y is varying now from minus infinity to plus infinity. This is something you would have come across in multiple places, right? And earlier also you would have come across this. So for example, let you call it, let I equal to, uh, it's just change of variable. So I am just reusing x also. I could have written this where x is a complex variable there. X need not be, yeah, x need not be as such a okay, the variable doesn't really matter. So if you want, you use z something else also, minus pi x square into dx. I could also write it as y varying from minus infinity to plus infinity, e power minus pi y square into dy. So I take I square now, I am multiplying it. Hope you understand the trick I am trying to do here. See, while I have something in the rectangular coordinates varying from minus infinity to plus infinity, see, if I am varying first for a fixed value of x
Sir,
here. Yeah.
sir,
Yes,
we
sir.
can simply tell that this is a PDF of a Gaussian, and then we can say that its integral will be equal to 1.
Yeah, that is also fine. That is correct. That's exact. That's very good. That's also absolutely fine. So this is a yeah, I agree with that. So even if you are doing it, let me also quickly do it this way. See, for example, the way we are trying to visualize it is, you are having, so I square would be, let me first write this out. X varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, exponential of minus pi into x square plus y square into dx dy. Now look at how it is there. Suppose you take a particular value of x, then this whole thing you are going through, right? Minus infinity to plus infinity of, so this is your y value. Okay, so you need to cover the whole space, right? That's what you are doing. So another way is if you are looking in terms of the polar coordinates, what you could do is same space you could also represent as saying you vary this r value, and for each r value you vary this theta value, right? Then your limits will become r limits will become 0 to infinity. So then e power minus pi y square 0 to infinity, you could write it out. So that's the basic trick. So what you do now for going from rectangular to polar, x equal to r cos theta, y equal to r sin theta. Then what is dx dy? This would be equal to r dr d theta. Just check this out. This is very standard one. So basically, if you want it the formula wise, typically what you would be doing is you have two variables now, r and theta both are there mixed together. So dx will be, if I am not wrong, you would be writing something like dou x by dou r into dr plus dou x by dou theta into d theta. Similarly, y is also a variable of 2. So you would do now dou y by dou r into dr plus dou y by dou r into dou y by dou theta into d theta. So something like this, you have to use this formula, okay, and use it. This is a very standard one. So you just Google it, you will find different proofs also. If you want some intuitive graphical explanation, that's what probably I'll try to give it quickly. So assume that this is your x and y. Okay, so let's say this is your r value. Okay, now you are increasing it this by dr here. Okay, now assume that this theta whichever is there, this also you are increasing it by d theta here, right? Now then essentially your this is what would give you the area now. Okay, that's what you need to find out when you are saying changing the ones. So this would be equal to, when theta is small and dr is small also, this is something like you could write it as r times d theta, and this area I'm giving you some intuitive one, this is not the rigorous one, but you could find it out. Just dx dy, the otherwise originally you draw in a similar lines for dx dy, and then if you come here, this would be equal to r times dr d theta. This is some intuitive proof. Okay, but again, you just Google for it, you will get more rigorous one if you want. This is the standard one. Okay, I right now for the time being I am directly using this. So my I square would be equal to, now what would happen with this, your theta would be varying from 0 to infinity, sorry, 0 to 2 pi. You are varying the theta from 0 to 2 pi. R would vary from 0 to infinity. And here you have e power minus pi times, what do you get there? Minus pi times,
R square.
right,
R
r
square.
square, and dr d theta. So d theta you could take out, right? You vary it from 0 to 2 pi, that would give you 2 pi. Then what is the integration for just r here? Anyone
E
can
power
quickly?
minus pi r square by 2.
Very good. E power minus pi r square by
2.
2 or something else?
2 pi.
Very correct. It's 2 pi. Oh, this r is taking care of this again coming, whatever is coming to r, right? This will be 2 pi. So then is that all or something else? E power minus pi r square by, still something is missing.
So limits from 0 to infinity.
Okay, that's there. Still something is missing.
minus
Right, minus 2 pi. So now what could happen? This and this would cancel. Now, so yeah. So if you are applying infinity here, that's becoming 0 minus, and then at 0 this is 1. Anyway, outside there is 1, so this would be equal to 1. Okay. Now I square is 1, so I also has to be 1. So earlier one, if you remember, f of kx was e power minus pi times kx square, right, into I was there. So that was now 1. So that's why the Fourier transform of e power minus pi x square is equal to e power minus k subscript x square. Now, another one is, for example, delta of shifting of the impulse. So these are the properties we would be discussing. What would be the CTFT of this? If you are
E
shifting it
power
by x, e power,
e power minus j 2 pi kx x naught.
very good, kx x naught. Now, suppose I am taking the other side now, okay? So to get the same thing, what I should do, you change a sign of it, change a kx to x and x to kx, and also change the sign. So you would be getting here e power j times 2 pi times, okay? And that you want k to be constant now, right? Because this is a function of x, so you made it as k naught. Now, what would be the CTFT of it here? Delta of,
Kx minus k naught.
right, good, kx minus k naught. The next one is, I have cosine functions now. I'm slowly coming into sinusoidal functions here. 2 pi k naught into x. So how do you compute the CTFT of it from based on the functions that we already computed? How do you write cos now?
E power j 2 pi
Sum of
kx
exponentials,
plus,
Right.
yeah,
So what would be the answer now?
complexes.
Power
What would,
j to
half
the
half
half?
times e power
Half
j
of
Hmm. E power.
j 2 pi kx k naught x
Oh, yeah, yeah. That's how you write on this side, in fact, right? Half of e power j 2 pi k naught x plus e power minus j 2 pi k naught x. That's how you would be writing on this side. So now that would result in here, this 1 by 2 would remain same. E power j 2 pi k naught x, you would make use of this property. Okay, so I could, for example, write it as, so if I'm taking this one, kx plus k naught,
plus k naught.
right, plus delta of kx minus k naught. I would like to do now same thing for sine of 2 pi k naught x. If I want, how do I write it here? 1 by 2j, right? So that would be minus j by 2, correct? So let me write it as j by 2, and internally let me change that. That would give me e power minus j times 2 pi k naught x minus e power j times 2 pi k naught x. Am I correct? So that would give me the CTFT will be e power j by 2 into delta of kx plus k naught minus delta of kx minus k naught. Is it not? So just let's put the how it looks like here. And it's anyway 1D, we could draw it. We have kx, right? If I write it as 1 by 2, what I am plotting here is imaginary part of, to be more precise, f of kx. If I am plotting it, this is how it looks like. Or yeah, if I'm, another word is magnitude phase, I could ask you to draw magnitude and phase also. Then magnitude both will be 1 by 2. Phase would be, you need to modify the phase part there. The one is right. So the other one was, what was this symbol for I'm using?
Impulse train.
Right, this is an impulse train. This is also referred to as Shaw function. They would be referring to it as Shaw function. And anyone remember any other name for it I was referring to? Blue.
Dirac comb.
Yeah, Dirac comb, right, correct, that's correct. So if you plot it, you could see it looks like the like a comb here, right? That's why they refer to as Shaw function or Dirac comb also, correct. Okay, so this, how did we define this out? This is equal to I varying from minus infinity to plus infinity, delta of x minus I. Any idea on what would be the CTFT of it?
Impulse train only, I think.
Impulse train only, that's correct. Let me write it as I varying from minus infinity to plus infinity. Then what here? Delta of,
kx minus
Minus I.
that's
Kx
right, delta of kx minus I. So how could I write it? This is nothing but comb function or Shaw function, okay, or impulse train of simply kx. So with that, I think we will now move on to the 2D part now. Two-dimensional CTFT functions. This definition also we covered in the video. So now what we would do, instead of using f of x comma f of x, we would now go to f of x comma y. How is it written now? How do we write it now? Integral over kx is varying from minus infinity to plus infinity. Ky from minus infinity to plus infinity. What should I have inside?
f of kx ky.
Right, capital F of kx comma ky multiplied with exponential of
J 2 pi
j
kxx plus
2 pi.
kyy.
j 2 pi times.
Kxx plus kyy.
Right, good. Ky y multi integrated with respect
Pkx
to.
dy ky.
Very good. Right. So let me now write the Fourier transform also here. Kx comma ky is equal to x varying from minus infinity to plus infinity, y varying from minus infinity to plus infinity, f of xy into exponential of
Minus j
hmm,
pi j 2 pi kxx plus kyy.
hmm,
Dx dy.
that's it. Right. Now there is something called as 2D box function. So earlier was 1D box function. This is referred to as, I'm looking at now few more examples here. So first I'll see examples, usually the extensions of 1D to 2D. So 2D box function here. Can you guess how it would look like now? 2D box function, what it means? Based on 1D box function, you tell me
Cuboid.
now.
Cuboid, sir.
Cuboid. So can you tell me the formula? So I would call it as delta, since it's a 2D, maybe again this box symbol is I'm using, since it's a 2D, I'm just writing 2 there. Of course, the moment I give two variables, that should be good enough. So how does it would look like? What is your guess now? How is it defined?
1 for x from minus 1 by 2 to 1 by 2 and y
Mm-hmm.
1 by 2 and mod y less than or equal to
Mm-hmm.
1 by 2.
Mm.
Otherwise 0.
Zero
Good.
otherwise.
Okay. Now I use, for example, this as one color and this as zero as zero. So as an image I want to plot. So how does it look like now here?
Square patch on the image.
Exactly. So this whole region is equal to, this is equal to 1 by 2. This is minus 1 by 2. This is again on y 1 by 2. This is minus 1 by 2. Inside its value is 1. Outside it is 0. Can you now tell me what would be the CTFT of it? Two-dimensional CTFT. I will skip even 2D from now on writing, because anyway this would tell you that this is 2D. So anyway, for the first time I'll write. Can you tell me what would be the CTFT of it? The
Sync
answer will be
kx into
okay.
sync ky.
Very good. Sync kx. Very good. Excellent. Into sync ky. Okay, we'll see why is it so. How could you write this function now? Can you write separate? Is it separable basically? Can you write it
Yes, sir.
as a combination of two 1D box functions?
Multiplication.
Right. So 1D box function of x, okay, and another box function in the direction of y. Is it not? So you think about it in this direction. So for example, you take x minus 1 by 2 to plus 1 by 2 when you are here, this is 1. Similarly, for this, anyway, it cannot, it has to be, if it has to, it's like a AND gate, right? This has to be 1 and the other one also has to be 1. This would happen only in this region. When y is equal to minus 1 by 2 to plus 1 by 2 only, it would happen, because you are having row of y. Okay, this you are varying. Similarly, on this side, this is 1 for the whole region here, but the other function rho y is 1 only for this region, when it is going to be minus 1 by 2 to plus 1 by 2. So essentially then you are getting a box here in the center. So probably the name box function makes a better sense when you look at this in 2D for a 2D function rather than the original 1D function. Is this
So,
yeah, yes, Shashwat.
so like in pi x of x, the box function of x, like for all the values of y, this thing is being extended out, right?
Right, correct. See, for pi x of x, what would happen if I just draw is, see, if I just take pi x of x, so then what would happen from 0? So this is all equal to 1 here for all these values, where you have, for example, here -1/2, here 1/2. This is your x. Okay. For all the, whenever I am drawing lines, you think that is equal to 1. Now, pi y is what's happening. It is 1 only for all these values. Okay. Where your y is, for example, this is 1/2 here on the y axis. This is your y axis. And this is 1 for all these values here. So if you look at the commonality, only during this, both pi x and pi y are 1. So only this region would come for you when you are multiplying them.
So,
Is it making sense?
yes, sir.
Okay, good. So I think we could generalize it and look at it as, for example, if f of x comma y is separable, then what we could say is you could write f of x comma y as some one-dimensional function. Let's call it as f subscript x of x, and another function f subscript y, which is a function of y. So in that case, your f of xy, the two-dimensional CTFT would be equal to your one-dimensional Fourier transform of this, right? And multiplied with one-dimensional Fourier transform of this ky, right? This is essentially, we are just putting it in a as if a generalized one that again comes from this equation. You can derive this from here. So the case we are considering here is, or you could consider here, the both are fine. Okay, so your f of xy, you could write it as, let's say, fx of x multiplied with fy of y. Okay, now this is a 1D function, this is a 1D function. This you could write it as, you could separate it anyway here, e power minus j 2 pi kx into x multiplied with e power minus j 2 pi ky into y, isn't it? Now all you do now is you take these two together and the other two together, and then you separate this dx dy. Then they are nothing but, this is nothing but definition of one-dimensional continuous time Fourier transform. Then I'll go to another, after this box function, other example I'll take a look at is e power minus pi of x square plus y square. Can you tell me what would be the CTFT of it? Now it's CTFT of it.
e power minus pi kx square plus ky square.
How are you able to do it? Can you do like any
I am separating them into x and y functions, and then
right? And you are doing it. And again, you could see here. Can you make it as a 1D function? Is it possible to make it as a 1D function?
Polar form.
Right, I could actually make it something like rho x square. I could make it. See, it is same as, for example, this you could write it as e power minus pi r square. So you could see here that this is two-dimensional function when you look at it in terms of x and y, but the moment you see this function radially, the same function is repeating for every value of theta here, is it not? So it's like you consider its value for so along all these points where this kx square plus ky square is constant, you would be getting the same thing. So it's in effect equivalent to a 1D function when you change the variables there. See, how does this function would be till here anyway? You yourself telling that this is the answer, correct? E power
Yes, sir.
minus pi kx square plus ky square. How does that would look like? See, if I am all these values, I take a circle here. This is my kx. This is my ky. Okay. At all these points, kx square plus ky square is constant, right? When I'm taking the radius, what is the radius
Yes.
here? Assume
Root
that
of
k.
kx square plus ky square.
Right. Of course, then you consider that particular way, the capital Kx, you consider, for example, this and that as small kx. So at all these points, this value is constant, is it not? So everywhere this function along this radius should have, when I move to circular coordinates, it should have same value, is it not? So when
Yes,
I
sir. Yeah.
when I move, do this change of variable, I don't have to worry about at what theta I'm looking at, because at all thetas, it doesn't matter once you know the R value. Is it clear now?
Yes, sir.
Good. So another interesting thing also here you could observe that a radially symmetric function, the Fourier transform of that function will also be radially symmetric. This is a very important property here, for the simple reason that anyway, while you are computing here, you could simply compute its value at just 1D case. You could consider R and theta, you go, and only at R you are computing that value. That way also you could see it. A radially symmetric function, if you consider it, okay, its DTFT or CTFT also would be equal to radially symmetric function. Is it clear for everyone? See, it is radially symmetric means any function given in x and y, you convert it to r and theta. So since it is radially symmetric, you just compute here in the r and d. If you look at, you just compute for one value of r. The theta is immaterial now. So the same thing would happen here also. So you just need to compute 1D transform there, and that it would repeat. So this is another important property. You just pay attention here. See, if it might be a 2D function, okay, but the moment it is a 2D function, you could and if given that it is radially symmetric function, you could write it in terms of r and theta. Now just your variables, instead of x and y, you have r and theta. And if I tell you that this function is radially symmetric, theta is just a dummy variable there. You don't have to worry about theta, because I'm saying it is radially symmetric. For every theta, you have the same thing. So you find out for it only, as it only depends on R. And then if you are looking at the output there, the output also would be radially symmetric. Just look at this function here, for example. This is a radially symmetric Gaussian function. And of course, it's slightly bit more next level of Gaussian, where I have divided by sigma square also here. And you already should be knowing by this time that if your sigma variance is high in the Fourier domain, that gets inversed here when it comes here. So it is in the denominator. In the Fourier domain, it comes to sigma square. I wanted to work you out, give it you as an example, but it's okay. So then what would happen is your function is radially symmetric here. This is how you would be getting it. Similarly, this is another function which is called as a circular disk. Okay, earlier that what we have seen is a box function. Now this function is this one, circularly symmetric disk function, it is called as. Okay, so again, just like this, what you get will be in terms of, they are referred to as Bessel functions. Okay, this is something very close to sync you will get here, which would be decaying as you move on. And you would see that the moment you are moving in the radial directions, okay, that values all would be same here. So the next example I would say is, let's say 1 is there here. What would be the two-dimensional CTFT of it? Delta of,
kx, ky.
that's it, kx comma ky. So how is it now? Let's say again we go to the 3D drawings now. Kx, ky, here you have one nail here. Okay, now of course then I could write the other way around. Delta of kx comma ky. Obviously take negative also, it would be same. So I would get here 1 now. sorry, I should be writing here x comma y, right? I should not be writing kx, ky here. I should be writing x comma y. Now, delta of x minus x naught and y minus y naught. Okay. So what would be the CTFT of it?
e
I
power
shifted one.
minus e power
Exponential.
minus j
Hmm,
2 pi kx x naught plus ky y naught.
very good. That's all. So how does this, by the way, would look like? Assuming x naught and y naught are positive. So let me call this as x. Let me call this as y. So where will be my impulse now? How many impulses
X naught
will
and
be
Y
there?
naught.
How many impulses will be there?
One.
Only one. Where is it located?
X naught comma Y naught.
X naught,
That's
Y
it.
naught.
Right. Assume that this is my x naught. This is my y naught. Okay. So here there is one nail here. That's your delta of x minus x naught. Okay. So then let me go back to cosines and sines. Cos of 2 pi times k1x plus k2y. What's the again before worrying about how it looks like in the spatial domain? So how would you proceed to compute its CTFT?
First we will convert into exponentials.
Right. So what? How should I write here? 1 by 2 into
E power
j
j
times 2 pi
2 pi k1x plus k2y plus
in,
plus e power minus j 2 pi k1x plus k2y.
right. Correct. So that's how it is there, cosines, and then what would be the CTFT of it?
Half times
Hmm.
delta of
Kx minus K1.
Delta of
kx minus
K1.
k1x
K1.
hmm,
Kx minus K1 comma Ky
kx,
comma. Yes,
k
sir.
kx, k
Minus
subscript x,
K1.
kx
Minus
minus
K1. K1
k1,
comma
hmm,
Ky minus K2.
very good, good, plus
Delta
delta
of
of
Kx plus K1
kx
plus
plus
K1
k1,
comma Ky plus K2.
yeah, I should not be closing it at,
Hmm.
comma,
Ky plus K2.
ky plus k2,
K2.
correct? So how does it look like now? Assume again this is my kx, this is ky, right? So how many impulses do I have now? Let me call this as quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay. And then in which quadrants do I have impulses now? Assuming my K1 and K2 are positive.
At 1 and 3, sir.
Very good. So this is, for example, K1 here, correct? This is minus K1. This is K2 minus K2, right? There is one impulse here and another impulse here. So now suppose I have a cosine on the Fourier frequency domain, then what kind of things can I expect here in the time domain?
impulse
Right.
impulses.
So you have impulses then here. So if so from impulses diagram itself, you should be able to now tell, for example, K1 and K2 are positive. In which direction is, so let me put two directions. Okay, let me call this as direction 1. Okay, I'm not anyway separating between going this and going this. Another, let me call this as direction 2. Can you check in which direction will be periodic in this case? So maybe it's a bit early for you to answer for all of you. So let's spend some time with understanding this cosine. Most of you, I hope, would have tried it at home. let's take with the first a simple function in 1D, which we are very comfortable. Let's start from where we are comfortable. Let me call it as 2 pi times kx into x. Okay.
That should be k
One.
naught, I think.
Very good. Sorry, that was my mistake. Good. Yeah. Now what is its value at x equal to 0?
1.
1, right? Now, of course, this would repeat, keep on repeating, assume that this is one period of it. So what is the periodicity of it?
1 by k naught.
Right, 1 by k naught. How do I know that? If you want, you keep it as periodicity cos of 2 pi k naught into some x plus x naught. You need to find out the smallest f naught for which this would happen. So for that to happen, you multiply each separately. So k naught into x naught should be equal to 1. So multiple of 2 pi, if you have it, that would happen, right? Or it should be 2 pi, right? Multiple of 2 pi it has to be. So 2 pi. That means your x naught should be 1 by k naught. That's one way of looking at it. Or even simple way is this k naught into x should be 1. After that, this would repeat. So k naught into x equal to 1. That implies your x is equal to 1 by k naught. Initially, it is 0. This would repeat when this again becomes 1. That's all I am looking at. So x is equal to 1 by k naught. From that onwards, yeah, this is a very that would repeat again. Now let's go back to 2D. So let's call this as fb of function x comma y, which is equivalent to cos of 2 pi into kx into x plus ky into y. This is the function. Okay.
K1, K2.
Yeah, sorry, I was making repeating the same mistake. So let me call it as k naught and k1. Okay, good. Now, is it periodic in x? First question. Assume
No,
that
sir.
k naught and k1 are non-zeros, right? Is it periodic in y?
No.
So is it periodic in at least in some direction?
Yes.
Right. So two questions are there. One is the orientation of it, and then the periodicity of it. Okay, these are the two questions that we would like to answer. So let's start with the periodicity part. How do you know what is the periodicity of it? Just similar to what we do here. It is so what we inferred so far is it is periodic in certain orientation, neither in x nor in y, but in particular orientation, in particular direction. So how do you know the periodicity of it?
Sir, can we take one variable like k naught x plus k1y is r, and
Then this is equal to n, this whole thing repeats because this is anyway 2 pi, correct? So when this becomes n, or if you want to be periodic, just the way you have taken here, you simply take k naught x plus k naught y equal to 1. Okay, that should give you the periodicity. So how do you get then the periodicity part? Let's say this y equal to minus kx, or I should be no, this is k naught and k1, right? K naught into x plus k1 into y. So minus k naught by k1 into x, right? Plus 1 by k1. This is along this line. This would be periodic. After that, so everybody next time onwards, yeah, well, let me keep n for a moment. So then what would happen? This is equal to n, okay, n by k1. So after every n equal to 1, 2, 3, and so on, this gets repeated. What I am saying is this would look y equal to mx plus c, where this is then 1. So all I am doing is just like to compute here k naught x equal to n here, right? K naught x equal to n in case of 1D. So when your x equal to n by k naught, that would keep repeating 1 by k naught, 2 by k naught, 3 by k naught and on. So this is, for example, if I take this whole thing, this is equal to 2 by k naught. So that gets repeated. In the similar way, k naught x plus k1y equal to n, where n is an integer, and then your y will be equal to minus k naught by k1 into x, right, plus n by k1. So now this is, for example, your x, this is your y, okay, and what is this value here? Can I, so this value, this is basically this graph I am plotting. So here y equal to 0, right? So that would be y equal to 0 means I need to find out the x value. So what would I get here? 1 by?
N by k naught.
Right. I'm just simply computing x-intercept and y-intercept. That's all. Okay. And what is the intercept here? 1 by?
K1.
K1. Yeah. By the way, substitute n equal to 1 there, because now we are looking at the periodicity itself. Okay. So now what would be this length now? This length would be equal to?
K naught square.
Right. Square root of k naught square plus k1 square divided by k naught k1. Now, if you find out this distance, which let's call it as L, okay, that would tell us with what value it is periodic. Okay, the distance to it we could tell. And if you find out this theta now, that will tell you in which orientation is this periodic. That's it. So aren't they enough to figure out this theta and L? Given this, won't you be able to find it out? So what you would end up here is very simple math here. Okay. L will be equal to, any idea?
Root k naught square plus k1 square.
Right. Very good. Did you work it out now?
Sir, it will be root, I think, not 1 by root.
Huh? L will be equal to 1 by root. Try it out yourself. I'm just giving you L directly here. And theta is very easy to find out. Theta equal to
Okay.
tan inverse of Shashwat has been telling it from the last class. Now he's silent.
K1 by k naught.
Yes. The same answer you are telling, right, Shashwat?
Yes, sir.
Okay, good. So that's all. These are the two values you would get. Very, very important things. So what it is saying is, you see, doing it is also very simple. This is theta. What is this value? This angle, how much? Maybe
90 minus theta.
theta. What is this angle?
Theta.
That's it, theta. This is if this is 90, this is also 90, right? This is 90 minus theta. So that is theta. One is you take this, the whole thing you take tan theta. Okay, this is 1 by k1 here. Okay, again got disappeared. So you know 1 tan theta there. Okay, so if you take tan theta there, that is giving you k1 by k naught here. Now this whole length you know. Now you take this, in order to find out this length, you take, compute tan theta here. That will give you one equation. You take one more equation by taking this triangle and compute tan theta. That will give you this length. You add those two equations and you would arrive at this length L. Okay, because in both of them you would be getting this length L. Okay, from that you would arrive at this expression. I'm sure with that you would be able to work that out. So the conclusion here is, the periodicity is oriented at an angle of tan inverse of k1 by k naught. Okay, that's where your periodicity you have to do in that direction. And the periodicity is 1 by square root of k naught square plus k1 square. That's all. So maybe I'll stop here. We will see few examples. See, you should be, for example, by looking at it, you should be able to say where its impulse would be. Okay, in which direction it is, whether it is an increasing frequency or decreasing frequencies here. Okay, in which direction they will be, how. So I could ask you things like, suppose given to this versus this, or in the same thing, if I am increasing this versus, you take these two. Okay, I might not give you absolute values, but you should be able to say whether they go far or near, in which quadrants they would be. That all you should be able to figure out. This absolute clarity you should be having, some intuition you should be having, even without doing anything on pen and paper or programming anything. By just looking at these graphs, you should be able to say how its frequency spectrum would look like. So if I'm increasing frequency, how it would look like. If I'm increasing kx, what would happen. If I'm increasing k naught, or if I'm increasing k1, what would happen. So take some time to contemplate on these aspects. Okay, so I will stop here.